All right, now to complete our discussion of frequency response here, we're going to move to filters, and we're going to talk about active filters. We've done the passive filters. We've done the resonance. All of this comes to play. We saw how resonance chose the frequencies in the passive filters, and those carry forward to active filters. The important thing about the active filters is that we're going to be working around op amps. And this really enlarges the sophistication and the capability. We're going to be just translating our passive filters into the active domain. But once you get into op amps, as your experience grows there, you'll see that active filters are probably the most common way to go. And passive filters will occur more as just like in power applications or in um, simple RC or RLC circuits. But usually they are attached around active components, either transistors, op amps, or something of that like. There is often a notion of the order of a filter. This is a first order filter that I'm showing here. And pretty much the only rule is that one of those two, you'll recognize from your learning on op amps in whatever chapter 7 and 8 back in there, that that in a simple op amp, the ratio of impedances between the feedback impedance and the input impedance is a gain function, and it is the operating type. If these are impedances and not just resistors, you get more than a gain. You'll actually get some frequency response, and that's what we're going to explore here. The order of a filter is often easily interpreted as how many op amps will it take to build the filter. But even that isn't a completely accurate approach. I'm not going to get too caught up in whether something is a first order or a 10th order or such. We're just going to build filters out of op amps. And a first order version is just a single op amp with some feedback and some input impedance. Okay? So the low pass filter as a first order, let's just take this. You can see the picture here. Rather nice, okay? It's just the feedback impedance is an RC circuit, a parallel RC circuit. The input impedance is just an input resistor. All right. Now, as we have always been doing to analyze, we just simply say, what is the input impedance, or what is the transfer function? I don't mean to say impedance, we're going to get to that, but what's the transfer function? What describes output versus input as a function of frequency? All right. So in this case, we've got, you can easily say, because we analyzed op amp circuits in earlier chapters, it's the feedback impedance divided by the input impedance. And because we're using the negative terminal here, we're talking about the minus sign down here, right? So all of that is kind of straightforward. Now let's just keep going then with our impedance. The feedback impedance, and I'm going to get my pen going here. The feedback impedance is what? It's just the resistor in parallel with a capacitor. So this is just the simple notation. Take the parallel combination of those two. Okay? And if we then do that, taking it the first step, here it is, the product over the sum, right? The product. All of these things, these basic ideas just keep coming back, whether it's resistors or impedances, they just get more generalized. I've always loved that. If you hang on to the first principles, you can always get more complex as things go on. The math just gets tackier, and you have to be more careful. Here we are in our what? Standard form. right? Right here, R1 plus j omega times whatever the constant is or needs to be. Okay, and we like that because it helps us identify what? By factoring out the RF over RI. Where did it go? Yeah, RF over RI. All right, we've got now, hang on, we factored it out here. Right, here we are. We factored out a gain term. Right, but this is now the transfer function HW. I just put the feedback impedance over the input impedance, which was RI, and this standard form just kind of anticipates what's going to happen over here. Okay, and that leads us very directly to, right, we're asking ourselves the question, what omega will cause this term, right? What omega causes the j omega RC to go to 1, right? It's the same question we've been asking over and over and over again, and we try to set it up. The standard form sets that up. And in this case, it's very straightforward, very easy, and here we have it right here. Okay? So that's low pass. Pretty easy to do, and you can just pick the values there for RF and RI for your gain, and the breakpoint is the 1 over RF CF. All right. Let's go on to the next one, the high-pass filter as a first order. And here it is, the simple op-amp. Only now to get high-pass, we put some RC circuit on the input, right? So we're going to have a Z in that's not trivial. In other words, the Z in won't simply be R in, right? So again, we're doing our transfer function. We got the negative terminal of the op-amp, so here's our minus sign right here. And then we've got ZF over ZI. So ZF is just going to be the feedback resistance, and ZI is the series combination of RI and CI. Okay, so to put this all together, here's our numerator. Pretty easy, right? Here's the denominator. This is what? Z input, and it's the series combination. Now let's just take a look at this before we move on. Think about what we've got here on an input. I'm a signal. I'm a sine wave signal coming in to this combination. And what do we know about capacitors? If I put DC into this, the current here, once the transient response passes, is 0, right? Because it's essentially an open circuit to DC. So we know right away in this setup, just visually, this kind of clues us in that this is going to be a low frequency block, right? When you put it on the input, this is like a low frequency block. All right? And at high frequency, the capacitor is going to look like a short circuit, the higher the frequency. So it only makes sense if you just look at this and one said, well, take a guess, is this high pass or low pass? Well, it's pretty clear it's going to be high pass. It's going to block the low frequencies because of that series case. Likewise, in the previous circuit, the low pass filter, the input was simply a resistor. So the input offers no block to frequency. DC is treated the same as AC low frequency, AC mid frequency, AC high frequency. So we can just think about it that way and just say, oh, this makes sense. I can recognize this, right? So I'm just saying, you can recognize without doing any of the math that this is going to be a high-pass filter. And it's a high-pass configuration. All right, so back down here now. Let's get back down here to the math. We're looking at RF, which is our ZF over ZI, and it's a simple case. All right, so all we have to do now is factor things around. Right, this was 1 over j omega c, so we got to clean that up by multiplying top and bottom by j omega c, and that's how we get to this, right? We multiply by j omega c top and bottom. Okay, and we're getting close here. This begins to look like something. That's our standard form, where we've got the 1 plus. And again, in order to find where are the breakpoints, right, we can say, what is it that's going to turn this term into a 1? Well, that's this frequency, right? Only now we've got it in the form of a simple pole and what? A 0 at the origin. All right, and if we go back to Bode plots and think about how this is, the 0 at the origin causes what? A break up. And then the simple pole at some other frequency causes a breakdown, right? And if I add these two piece for piece, I get this, right? So I can just sort of look at this function and the Bode plot of it and see what's going on. Now, this point right here, this corner is the origin, right? Because we don't have 1 plus j omega something or other here. We just have j omega at the origin. And this is the simple pole. Okay, and as you work with these things, you'll get to recognize that stuff, you know, as it comes along, rather than always having to go through the math. All right, so now we've got a bandpass, a notch filter, right? So this is something that, as we've looked at before, it is going to pass certain frequencies, not low frequencies, not high frequencies, but a set in the middle. And we saw this as a resonant circuit earlier, back in the passive filters, or the passive, we saw it in the resonance first. So all we're going to do is capture that idea and make it into a filter that works for us. We did it with passive filters, now we're going to do it with active filters. Okay, so let's take a little time with this one. I want you to see pictorially what's going on here. All right, so let's start with just the frequency range, and I've left the bandwidth and the omega 1s and omega 0s and omega 2s on here. And let's just say we have a whole set of frequencies. Here they are, a whole set of frequencies that come trotting through here, all at the same amplitude, the K magnitude. Okay? And now let's say piecewise we just put together one filter. Let's say if we could knock off the upper part, all right, and not let it go on out to infinity. And we'll do this at some frequency called omega 2. All right, what we have now right here, so far this looks like a low pass. Whoops. Okay, that's all we've done is got a low pass. And we have half of the filter already designed if we think of it as a low pass. All right? Now if we go with that, we say, let's just make a block that says, we're just going to call this block up here a low pass filter. And we don't know how we're going to build it. And we go on down because, we've already had this in the previous slides. We're going to say that stage 1 is a low pass filter, and it sets W2, right? Now we're going to do that first. Okay? And as we think about it, we don't really need to get all wrapped around the design down here. We can just think of things as block diagrams. All right, now if we look at the lower portion of this, and this were all here, let's say we didn't have the high pass, this kept on out here like this, we would have basically a high pass filter. And if we recognize that, it says the high pass can set our lower frequency point. All right, put in a block, add that circuit because we know how to do that, and that sets our lower part of the band curve. Okay, that's what's there. All right, so these two pieces, now could we have reversed them might be a decent question. We recognize now that this whole frequency function up here, this whole frequency function is made up of a high pass, and a low pass. All right, and they're put together. We did the low pass first. Could we have done the high pass first? And I hope you can just see visually, no, you need to do them in this order. Because the first thing you're doing is clipping off the high frequencies. If I clip off the low frequencies first with a high pass filter, then it's too late. I've already lost all this down here. So things need to happen in a certain order, and that to me is one of the nice ideas of showing it as a block diagram. You can do this step first, okay? You do the blocks first, and then you can go fill in the circuits. Right? And this is like top-down thinking. And it's an important, just conceptual form of how to work with advanced circuits and advanced circuit analysis. All right, there is a gain term, so we're treating these as blocks. And there is a gain term that we'll just put on as in the form of an inverter. And notice what the values are down here. Where are we? The values are RF and RI. All right, just the simple gain term, and it's a minus amplitude. Now, if you needed a plus, of course, you would have to add a unity inverter after this. But the nice thing again is, look, these blocks, each block represents a circuit element that happens in sequence. And you build the blocks, and then you build the circuits in the same order, and they perform the same way. And if it doesn't do the right thing, you can think about at the block level what should have happened or what you want to have happen. Kind of important to get this thinking down. Okay, let's take one more look at this before we leave. This has all been the picture approach, and let's just finish it out with a nice look at the math. So here's our transfer function, which literally we haven't done yet, right? We analyzed the circuit in terms of its low pass and high pass elements. So let's just finish that by taking a look at the transfer function, V out over V in, the way we'd like it from the math. So we made a low pass portion. The low pass was what? A simple pole. So that's not a pole at the origin. It's just a simple pole out there someplace, right? So what have we got? What's going on here? This is going to determine omega 2, right? Then we added another term, which was the high pass term. And the high pass, remember when we did that active filter, it contained a 0 at the origin. 0 at the origin. and a pole, right? Right? So this, you can imagine, this is going to be our omega 1. It's going to be the first breakpoint. All right. And then I'll have written over it a little bit, but then we've got the inverter, which contains our, we factored this out. This was our gain term. It's called an inverter because it was an inverter function, but this was the portions that we factored out, right? So this is all in the math. We can follow through some more. Oops, I may have to convert here, convert my guy, and get an eraser going. Let's see. I want the eraser, so we may have to come over here and erase a lot of this stuff. Right? We can get rid of this so we can see that nicely too. All right. So now we have our get back to what I want. Here we are. So now if we just multiply all this together, in other words, we're working it backwards. We started by recognizing functionally first a low-pass filter followed by a high-pass filter. Do those things in sequence. Now we're going backwards and saying, does the math support that? And here we are taking those ideas, right? The low-pass idea and the high-pass idea in the inverter, and we're going to multiply them together, put those functions, and I've reordered them here, or the book has. And we recognize omega 2, the outside one, is a function of C1, right? Here it is here. The omega 1, which is the lower frequency breakpoint. So these two now determine the bandwidth. And this center frequency is the same as it has been before. Right? This is all the same as to way back in resonant circuits. And the Q is still a function of these two omegas, so it's a function ultimately back to R, C1, and C2. Okay? Deliberately chose R to be the same here, you'll notice. That's not a mandatory thing, but you know, it just makes it cleaner and easier when you try to put things all together. All right, so here is that transfer function now, all in this form in terms of our omega 1s and omega 2s. Right, and now if we jockey it around again, we keep doing this, we get our magnitude. Right? In this form, we can now extract the magnitude of the whole function. That's all we're going for here. Right? The magnitude of omega. And so it's the magnitude of this whole piece. And how do we get that? Well, we've got our omega 1 plus j omega 0, omega 2 times this. So if we follow through all the math, and remember, we're going to be substituting this in when we need to, because this is going to produce an omega 1, omega 2, and this is going to produce omega 0, omega 2, and omega 1, omega 0. So we're going to depend on this substitution a lot. And when you get done doing all that, and then factoring out the remaining omega 0, you're going to get this term. Okay? So that's our magnitude. And this means there's a gain term at the center frequency and around it over the bandwidth that is this. It's a function of the original gain, the constant gain, plus one that is frequency dependent, right? But it's dependent on the design parameters. It's not going to, this is not going to vary with frequency, right? This is not a, when I said frequency dependent, I probably expressed that wrong. These are constants. Okay, omega 1 and omega 2. Those are constants. But they play a role in the flat out gain of the transfer function, right? So when you get to the middle of things, you're going to have that constant gain. All right, let's use that same thinking again, if we might, and look at the band stop or the notch filter. And it is in this shape, this picture out of the text. So this is a fairly narrow bandwidth the way they've drawn it, right? If this were to be a deep notch, let's say, where are we at? If this were to be a deep notch, right, it would be coming way down here. But let's not worry about that right now. Let's recognize what we do have. We now know we've got something that looks like our low pass going on here, and here's our high pass. So this part is low pass, and this part is high pass. Only now we've separated the omega 1s and omega 2s, so we're going to end up with the notch in the middle. So how do you suppose this is going to happen? Well, let's just do the usual stuff with the transfer function. Right, there's our gain as a function of the feedback resistors. And here's the two terms for high pass and low pass. Right? And let's go back to the blocks again. Okay, so look at this. Look what happened here. We now have our gain. And now we've got the sum of two terms. Remember, in the last approach, we had the product of two terms, right? In the, I can maybe make a note up here. In the band pass, we have the product of low pass and high pass. So we had to have them in order. Okay, now to get the notch, we look at this. We're simply saying, I want to allow everything that's low, and I want to allow everything that's high. So all I need to do is add two filters, a low pass and a high pass. So the idea in the blocks is, let's build this as blocks first. Okay? So here's our low pass now creating omega 1. Remember, in the band pass, the low pass created omega 2. And here we now have the high pass is going to create the high frequency side of the notch. And all we're going to do then is sum them. Okay, so this should make sense. And look, it shows up nicely in the math. We've got the transfer function we want has some gain, and it's got here what? This is going to be the, as long as the frequency stays real low, this is going to stay 1. As soon as the frequency gets high, this term is going to dominate. So this has to be the low pass. And here we have what? When the frequency is low, right? This is a 0, so it doesn't matter what's going on here. And then as the frequency gets high, this term swamps the 1, and you end up with 1 over 1. So that's going to be the high pass. Okay? So the response just follows that. This is a summing function, so we want to do summing up here. Remember in the last one, when we put the whole thing together, we actually put together the products of the terms. It's important to see the blocks as representing the math, right? This math over here, this math is well represented in that block. Okay? And then at that point, then you can go to the circuit. Now this looks awful compared to, at first glance, this looks awful compared to the previous one, but because those were nice blocks set out, first the low pass, then the high pass, then the gain. Here we don't have that. We have summing, but we've done summing junctions before. If you cut this off here, right, this summing amplifier would just be summing input 1 with input 2 with equal gains, RF over RI, right? You remember back from op amps, if we wanted different gains, we could just change the input resistances. So, and here are our breakpoints established by, here's the low pass filter up here. Right, that's the low pass. And the high pass is the one down here. Right, so back to putting together circuits and our op amps. All we're now doing is, instead of putting simple AC or DC or whatever signals in, we're now saying, oh, I'm going to condition that signal. And because we're conditioning the same signal, we put the same signal into both the low pass and the high pass. So this is why I go back and encourage, think about the blocks. Think of it as blocks. Think of the mathematics as block pieces that you're putting together. And decide, am I doing them in sequence? So are they multiplying? Am I doing them in parallel? So are they summing? This is what we want to achieve. Okay? Now, let's get the gain and the center frequency off of this notch filter. All right? So here we have the transfer function, and lots of math going on. We can just grind this around, but we're used to this by now, right? We just look at, what are we doing? To get this math to present, we're going to be multiplying. Both of these have the similar looking denominator here, except for omega 2 and omega 1. Right, so we're just going to be multiplying through by something that relieves omega 1. So we're probably going to be multiplying through by an omega 1, omega 2 term. Okay, and that's what's happening here. If you look at the top, what have we got? We need to clean up both of these denominators. So they're going to have to be multiplied by 1 minus j omega over omega 2. And a 1 minus j omega over omega 1. Something of that sort. Anyway, that's just math cleanup. We've gotten good at that sort of thing. When you do that, we have a constant term. There's our RF over RI. And remember, this RI was what? The summing input resistance, right? It's not the one that's part of fixing omega 1 and omega 2. All right. So now the transfer function, the magnitude we're looking for is this is just a whole lot of repeat of what was up here, right? Except with absolute magnitude signs around it. All right. And if we drag through all that and go through all that, finding out the magnitude, right? We do that, we're going to end up with something that looked very much like the one before, except it's got 2 times omega 1 in the numerator. Okay, so that's math, and I'm not going to keep grinding through all of those pieces because they are very much the same as they have been before, right, with the all of the Q's and the bandwidth and that sort of thing. All right, let's do a couple of problems. This is one, design a high-pass filter with a high-frequency gain of 5 and a corner frequency of 2 kilohertz, and they say use a 10th microfarad capacitor in our design. So let's take a look at this. All right, so high-pass filter, right? By now we know as an active filter we're talking about this. Talking about a resistor. There's our capacitor into the op amp, the negative side, right? And then some feedback resistors. So this is a really straightforward design. So what do we know? The gain is 5. So 5 is equal to R of the feedback divided by R of the input. This is RF, and this is RI. Okay, so I'm just going to say, therefore, RF is equal to 5 times RI. Obviously, the trick is going to be to find either one of those. All right, the corner frequency is 2 kilohertz. All right, so what does that tell us? Well, the omega at the corner is 1 over what? This input combination, so it's RI times C, but that's 2 kilohertz, and we've got a 10th microfarad capacitor. All right, so what is this? This is going to be 1 over, we don't know RI yet, so we'll just leave it at that, times the capacitance, which is what, 0.1 times 10 to the minus 6th, and this is going to be equal to 2 kilohertz, so that's 2 pi times 2 times 10 to the third. So what is this going to get us? This is going to get us RI. So if we solve all this thing, we'll get RI is equal to, looks like 4 pi times 10 to the third. Wait, I'm going to be doing this backwards. It looks like I'm going to be having this whole thing on the top becomes 10 to the 7th divided by 4 pi 10 to the third. Yeah, so that's going to be equal to 1 over 4 pi. 1 over 4 pi. All right, equals, let's see, where am I at? So it looks like I'm going to have 10 to the 4th over 4 pi. All right, this is about 12. So I can get my calculator out, but I know this is about 800 ohms then. All right, 4 pi is a little over 12, and 10 to the 4th divided by 12, it would be like 100 divided by 12 is about 8, and 2 left over. Yeah, so this is my RI, and RF is equal to 5 times this, so 4K. Okay? Oh, and that's what they have down here. That's what the answer was. It's probably a little different than the one in your text, but it's the same idea. All right, let's try number 13 in the same way. We got to design a notch filter. So similar sort of thing here. Design the notch filter with these specifications based on 1447. But 1447 is our standard picture. All right, now I'm not going to repeat that. It's you know, the one with all the summing pieces, right? So we'll do the 2 blocks, right? It's this, it's this. That's that complex picture, right? So this is the sum here. All right. So mostly this is you know, plugging into the various formulas, and we've got our RIs of 10K. Oh, and the R's are also 10K. That's very nice. And we know the Q, right? A lot is known here in this thing. So so that means the feedback with, let's see, we've got a gain of 5 up here. So what was that? RF over RI. Whoa, I is equal to 5. So that means RF is 50K. Okay, so we got 50K for RF. We know that now. And let's just go find the corners then, right? Omega 1 is 1 over, what is that? RC1. So in the notch filter, the omega 1 relates to that capacitor, so it's RC1. All right, and we need to know where is omega 1, right? So where is omega 1 and omega 2? Okay, so I should say, where are they? All right, but we know those because we know the Q, so we can find the bandwidth, right? We know that the bandwidth is the center frequency over Q, right? So, whoops, we don't want that. Well, yeah, we do. We want the center frequency, which is omega 0, 20 kiloradians per second, divided by Q of 10. So the bandwidth is 2 kiloradians per second. All right, so that means omega 1 is going to be 20 minus 1, 20 minus band over 2, which will be 19 kilorads per second. And omega 2 will be 21 kiloradians per second. Okay? So this is not difficult. Once again, then, we're back to just chugging. We can take this guy and put it over here and follow through. We've got 19 kiloradians per second is equal to 1 over, and they nicely gave us the R was 10K, so this is 10 to the 4th times C1, meaning C1 is what? 1 over 19 times 10 to the 3rd times 10 to the 4th, so 10 to the 7th. And if you grind all this out, you can you'll come up. This is about 20, so we know it's going to be something a little bigger than 5, and it's going to be 10 to the minus 7th in the numerator. So if we made this 0.19 and made this a 9, right, we will have about something bigger than 5 on the plus side, nanofarads, right? And you can go look at the real number. Yeah, here they are down here. You've got 5.263. All right, let's do the same thing. Pretty much easy with omega 2 is a 1 over R. Same thing, we'll just rush this along. 10 to the 4th times C2, right, times C2. And that will be, gives us what? C2 is equal to 1 over omega 2, so that's going to be our 21 times 10 to the 4th, third, times our 10 to the 4th. So it's all the same thing. So we know it's going to be very near this, right, except a little smaller. So this is going to be 1 over 0.21 times 10 to the 9th, right, which is going to be, instead of 5 on the plus side, it's going to be 5 on the minus side. So we'll call that 4.8 nanofarads. Okay? So those are the 3 values that were being looked for, the C1, C2, and the RF. Okay. Now I want to close this chapter with really just a short piece on scaling, if I can. And scaling is really kind of a straightforward thing. We're going to scale magnitude, and then we can scale frequency, or you can scale them both. Okay? And really what we want to do for magnitude scaling, right? All we have to do, the magnitudes, the magnitude of the transfer function is really just if you scale the impedances, right? So we're going to want a scale factor. And I'll just use the one the book uses. It's handy. Some constant that we're going to scale the magnitudes by. And frankly, all we're going to do here is scale. We want the new impedances to be K sub m times the old impedances, right? So if it's a resistor, you just got K sub m times R, right? If it's an inductor, right, Z of the inductor will be what? K sub m times Z sub L, but that's just J omega Km times L. All right, and finally, if we want Z prime of the capacitor, we'll do the same thing, K sub m times Z of the capacitor, right? So that ends up, obviously, 1 over J omega C over K, right? K sub m times Z sub 1 over, this would be K sub m over J omega C. But as the capacitor, we want to break it down in terms of the capacitor. We're really just going to have J omega C divided by K sub m. I took the K sub m that would normally be up here and I flopped it down here. Because what I want to illustrate is you're going to get a smaller capacitor. You're going to get a bigger inductor. And you're going to get a bigger, this is assuming K sub m is greater than 1, right? So this is kind of intuitively correct. If all I'm scaling is magnitude, if I do not want to move the frequency corners of anything, the ratios have to remain. The RC ratios have to remain, and the RL ratios have to remain. Okay? Otherwise, frequencies will move. Okay, so that's gathered together here. Pretty easy. This ends up with the nice result that the frequency doesn't move. All right, now we want to do frequency scaling. Right? We have a similar thing, except what are we going to do? We want the new omega 0. We want the new omega 0, yeah, the whole frequency spectrum to move. I mean, what we're really doing is we're saying we want omega prime to be some constant of frequency times the old omega, right? That's what we're going to want to have happen. So the resistance term is not a frequency-dependent term, so it isn't going to show up in here, right? R is not a function of omega. So all we care about is the two terms that are a function of omega. So here we have, and that's the inductor and capacitor, of course. And so what we really want to say is that J, make this substitution, that J omega prime, right, times some new L has to equal our old J omega L. Right? So we have a new omega prime, so this is our J KF omega times some new L prime is equal to J omega L. And if we clean all this out, we're going to find out that L prime, our new L, is going to be equal to the old L, now this time divided by our scaling constant. All right, we can try a similar thing with the capacitor here, of course. And we're going to say we want to set the capacitor impedance. Where's my pen? I need to find that first. We want to set the capacitor impedance 1 over J, omega KF times C. Well, what's happening to my pen? KF times omega times C, right? And this needs to be equal to 1 over j omega c. Whoops, this is our new c. It's going to be 1 over j omega c. Okay, and if we do all the cleaning up here in the same way we just did, we're going to get what 1 over kfc is equal to 1 over c. Right? So keep my primes in here. So that the new c prime is going to be what? C over the frequency scale. Now that's interesting because that's kind of how the magnitude scaling went in terms of the capacitor. Okay, so to do frequency scaling, all we change or watch for is the capacitors and inductors. And to get the new values, we divide the existing values by our scaling constant. And so here's all that summarized. No surprise, we just did that. But now the important thing is what? The frequency moved. Omega prime moved. All right, the frequency moved. And it moved in some scaled fashion. It didn't translate all shift up or shift down in frequency. Everything expanded or contracted by the scaling player. Okay? And if we want to do them both, right, you can follow through more of this math, but the resistance is only a function, whoops, here we are. The resistance is only a function of magnitude. The inductance is a function of magnitude in the numerator and frequency in the denominator. Right? So you'd get some scaling constant of its own if you're doing both magnitude and frequency. And likewise in the capacitor, except both of them are in the denominator. Right? And the frequency is only affected by the frequency constant. So there is that. And here is, I'll do this. So really, the point of this is if you just keep track or refer to these, and if you're only doing magnitude scaling and not frequency scaling, set kf equal to 1, right? Kf equals 1 for magnitude only. And likewise, km equals 1 for frequency only. Okay, pretty obvious. All right, this is what we'll do. This is chapter 14. Some things to digest, but I really want to stress between Bode plots and block diagrams and piecewise putting together high frequency, high pass, low pass circuits, you can synthesize the others that you need, the band pass and the notch, the band reject. You can piece that together out of the simple high frequency and low frequency components. And that idea is reflected, again, as I say, it's reflected in Bode plots, that you can sum individual breakpoints and keep that going. And so the Bode plots, to me, reflect or carry forward right into the whole block diagram approach of filter design. Okay, so that's it for chapter 14.